안녕하세요 여러분, 혜리입니다. So in the previous video we have seen the definition of integration. So we used something called the Riemann sum, and we also looked at how the Riemann sum is related to the integration. So one thing is that you guys don't have to know what exactly Riemann sum is, and you don't need to know the application of it, but it's good to know the definition of the components of the integral. So for example, dx and fx and all the sine integral, what do they mean? So yeah, it's always better to understand what you're learning. And we mainly look for the indefinite integral in the last lecture, and I told you that for various methods of integration. So if you're in IGCSE students, you just need to do antiderivative, and for SL you need to do until substitution, and HO you have to do a bit more, so by part and some other like strategies. But for IGCSE students, I recommend you to also study substitution first, because it's going to be very useful to learn and apply in the questions that you will see. So we have seen the basic integration methods, so integrating x to n and all these basic formulas. So now what we're going to start with today is we're going to look at some other functions, integration of other functions. So further. So we are still going to use the concept of antiderivative. So the very first thing that we learned was this, right? So that's the first thing that we learned. Now today we're going to do some other functions like trigonometric functions, exponential, and logarithm. So again, we're going to use the concept of antiderivative. So remember that in differentiation, so if you have to differentiate a function, and if you get the answer, so once the function is differentiated and if you get sine x, then that must be the integration of sine x. And what can you think of? So for example, if we had, so that's for differentiation and that's for integration. So let's recall some of the differentiation formulas. So if we have y equals sine x, and if we have to differentiate sine x, then we have cosine x, right? That means if we have to integrate cosine x, we have sine x, right? Because it's the concept of antiderivative. So once you integrate a function that is differentiated, then you'll have the original function. So that's what it means. Cosine x integrate, then you have sine x. Okay. And similarly, we had y equals to cosine x, and if we differentiate cosine x, we have negative sine x. Right? That means if we integrate negative sine x, then we'll have cosine x. For tangent, you don't have to know, but if you're in HO, you have to know, but I'm going to talk about that later. And two more, so not trigonometric, but logarithm, so natural log, and if you differentiate it, you'll have 1 over x. That means if we integrate 1 over x, we will have ln x plus c. So then some may ask, so 1 over x, we can write it in the form of x to power n, right? Because 1 over x is simply x to negative 1. Can we apply this? No, because see, n equals to negative 1, that means the denominator here is 0. So you cannot integrate x to -1 using this method, okay? So we have to use the concept of antiderivative to do this. And lastly, exponential, so e to x. Then we have e to x, right? Then if we integrate e to x, we have e to x. So these are the four main things that we have to see. And if we write this, rearrange this. So if we integrate sine x, we'll have negative cosine x plus c. So remember one of the rule that we learned. So if we have a constant, then we can just take out the constant, right? And we can move it to the right hand side. So we take out the constant outside the integral and then move it to the right side. Then we'll have negative cosine x. And also, if we move negative sign to the right hand side, then some may think that it's negative cosine x minus c, right? But as I said, c is so c represents the integral constant, which is just an arbitrary constant. It can be anything, so we can just say negative c equals to c, right? Maybe this is a capital C, whatever. So it doesn't really matter. So if we write this again, we have these four basic rules of integration. And I'm pretty sure memorizing these formulas is not that difficult. So that's it for the basic rule. And for all IGCSE, SL, and HO students, so using chain rule, we could, so when we had to differentiate something like this, then what did we use? We used chain rule to do it, right? So we substitute 7x as some other variable u, because we certainly know how to differentiate sine u, but not, sine x, but not something like with a coefficient. So we let 7x be u, and then we differentiate it using chain rule, right? And that was simply this. So that means if we have to integrate cosine 7x, okay, first, if we integrate 7 cosine x, 7x, then we'll have sine 7x plus c, right? And as mentioned, the constant, we can move it out, and then we can move it to the other side. So we'll have something like this, right? And why does that work? Because again, it's so simply for integration, we're just using the antiderivative. But if you can think of it more, this 1/7 is in fact, so if we let that as something like x plus b, let's say, if we have to integrate cosine ax plus b, then the answer would be sine ax plus b plus c over 1 over a, and this a here is the derivative of ax plus b. That's why we have this result. And so the reason why I'm going to this I moved to this example directly is because you can use the concept of antiderivative to do this. But I'm going to teach you another method of doing this, which is more generalized, so that it doesn't need any like inspection. So again, this is solving by inspection. So we start with a new integration method called the substitution. integration by substitution. So what does that mean? It's very, very similar to chain rule. So the main reason of using chain rule is because we don't know how to differentiate it given what we know, right? That's why we rearrange the equation into something that we are more familiar with, right? So clearly we know how to differentiate sine x, but we don't know how to differentiate sine something with x, a coefficient with x. So what we do is that we let a variable be 7x and make it into this form, right? Because x, it's exactly the same form, no coefficient, just coefficient as 1 in front of the variable. And we use chain rule to compute the derivative. So how we can use substitution for this question is so same thing as I said. So if we have something like this, sine ax plus b, we don't know how to integrate it, right? What we know is we know how to integrate just sine, but not a transformed version of sine. So what we can think of is that, again, use substitution. So let u be ax plus b, let's say. Then we'll have this, right? Because ax plus b is now u, so we replace ax plus b by u. Now again, as I mentioned in the previous lecture video, so if this means we are integrating sine u by x, and again we can see that the variables are not synchronized. So what do? We try to synchronize the variables. So we have to find this as in du, right? But again, we can't just replace dx by du because that's affecting the equation, and the equality from here to here will no longer hold. So what we can try is that we try to use this to find the relationship between du and dx. And how do we do that? We simply differentiate this by x. What does that mean? So if we differentiate u by x, then that's what we will have, right? d over dx. And the right hand side is simply differentiating ax plus b by dx. And this would be very simple. So b is a constant and we're differentiating by x, so just disappear. And this ax will have just a constant a, because if we differentiate ax by x, we'll have a. Now du over dx is not one variable. Du is just du, dx is just dx, and it's just a quotient form. So what we can do is that we can rearrange this so that dx goes there and a moves here. So du over dx equals to a, that means du equals to a times dx. Hence we have dx as du over a, right? Rearrangement. Then we now know that dx can be written as du over a. So let's apply that. And this 1 over a is just a constant, right? Then we can take it out. And what is this? It's simply this, just the variable being u, right? So that means if we have to integrate sine u by u, we'll have negative cosine u plus c, right? So negative 1 over a cosine u. Oh, and one thing, so here we have 1 over a times c, right? But again, c is just an arbitrary constant. We can just make another c. So okay, for example, if I use the capital C here, then I can just let it as c1, right? And we just need to change u back to x. So this is how we can use substitution to solve this. So like this example, if you could solve it by inspection, so using the antiderivative, which isn't that hard, it's better to use this, to be honest, because as you can see, it doesn't take much time. But substitution, often it may take at least longer time than solving by inspection. So it depends on you. So if you want to make it as a general formula to do it, then you can use substitution. But if you want to do it just by inspection, then that's also fine. That's absolutely fine. But later, not for GCSE, but for SL and HO students, you will have a question, integration question that has questions that have to use substitution. So, but it's not the case right now. So we've done sine, so we have cosine, and doing exactly the same thing, and also we already have the result out. So again, you guys can try it by yourself. So if you want to practice substitution, you can use substitution again to derive this. Okay, and also okay, E2. One thing for logarithm is that okay, actually it's the same. So if you have to differentiate that, that means it's just ax plus b, and it's a plus c. Okay, logarithm, I'll explain it a bit. So how we can do this is that, again, the same. So we know how to integrate ln, right? Which yields 1 over x. I mean, if we know how to integrate ln x, right? Just ln x. Then we have 1 over x plus c. No. What am I talking about? Sorry. Okay, integrating ln is much harder than what you think. We have to use something called the integration by part, and you'll not be asked to do that. So this is the opposite. So for example, what I was trying to do is this. So what do we have to do if we have to integrate that? So again, we know how to integrate 1 over x, right? If we integrate 1 over x, we'll have ln x. But what if we have a linear function in the denominator? So where you don't have a plain 1 over x, and instead a transformed linear function. So what we can do is that, again, we let ax plus b as u, and we do the same thing. So by rearranging this, we have du as a times dx, and change everything to the substitution you made. So you'll have that. That means it's just so move. Du. So this coefficient a, the constant a, we can make it out, move it out, and integrating 1 over u by du is just ln u plus c, and we have this, right? So we can see that if you're not really good at solving by inspection using the antiderivative, you may use substitution, and it's gonna be much easier for you as you can generalize the steps. So these are the formulas for the linearly transformed functions that we've seen, right? So that's it for GCSE students. But as I said, I'm going to mainly talk about substitution now, and I strongly recommend GCSE students to study substitution as well. So if you want to, you may keep watching this. So more application of substitution. So the previous examples we've seen are the cases where we could just solve it by inspection, and now I'm going to introduce some examples that you may not be able to use inspection to solve. So for example, something like this. So sine to 7 times cosine x. So in differentiation, if we had a product of two different functions, then we could use product rule to differentiate it, right? But for integration, when our functions are multiplied or divided together, often they are much more complicated than differentiation, because again, integration is the idea of antiderivative. So this means that you have to think of a function where if you differentiate it, you have this, and it's not easy to think of. So what we can try is that we can use substitution to solve this. So the main part of integration by substitution is that it really depends on what you can substitute. So, and there are not many options to substitute, and if you do a wrong substitution, you don't get the answer. So integration is more restricted than differentiation. So for this case, I'm going to do two ways of substitution. So one, I'll substitute sine x, and the other one is I'll substitute cosine x, and I'll see what happens. I'll show you what happens. So first, let u be sine x. Then we have u to 7 times cosine x times dx. And again, mainly we have to integrate this u. So what we can try is that first we can think of switching this dx into du by differentiating this. And then by rearranging this, we have equation of dx in terms of du. So we can replace this back. And magically, cosine x cancels, right? And it just yields u to 7 du. And now everything is done for you. So it's in the form of x to n. So what we can do is that we add 1 to the power and then make it as a reciprocal. And that's what we have. Now, I'll try the other example first. So now we substitute cosine x to solve this. Then if we're doing the same thing, so we leave sine to 7, and cosine x becomes u, and it's dx. So again, we try to write dx in terms of du, right? And putting this back in. Alright, so I hope that you guys can see the difference now. So the main difference here is that if we substitute sine to 7, if we substitute sine x, which has a higher power in the function, in the given function, then we can see that we can kind of cancel out cancel out the unnecessary part using the derivative, right? But here, well, we can cancel, although we can also cancel, but we can't cancel the entire thing, right? We still have sine to u. And from here, if you know some trigonometric identities, where, for example, we know that sine squared equals to 1 over cosine squared. So you can try to use it as by cubing both sides. We have sine to 6 as 1 minus cosine squared to the cube, right? Then you put that in and then replace cosine x squared as u squared expanded out, and then again multiply by u. Then you'll have an equation, a polynomial with in terms of u. Then that's how you can integrate it. But as you can see, this method is much easier than this, right? So depending on what you can substitute, you have entirely different steps. And how can we make a better substitution? So what I'm trying to say is that no matter what you substitute, you may be able to find the answer eventually. So not all the case, but most of the case like this. So even if you substitute cosine x, you can have the answer, but it's just the matter of time. It will take much more time than the first substitution. So what I strongly advise you to substitute is the first. So tips. First, substitute something that has a higher power. So I'll give you some more examples, but yeah, so from here, we have sine x and cosine x, and clearly sine x has a higher power, so we could think of substituting sine x. Second, the most important thing is that if you want to substitute something, then the derivative of it must be inside the given function. So what does that? So first, so what I'm saying is that, so see, we wanted to substitute sine x, right? But you can see that if we substitute a function of x by another variable, we have to, no matter what, we have to synchronize the variables, right? And in order to change this dx into du, where what we need, which is what we need, we can see that there is always the derivative of what we substitute in the denominator, or it could be in the numerator depending on the function. But yeah, one thing is that you will have the derivative of what you're substituting. That means that is undesirable to be in the part of what we rearrange, right? So if we have a derivative of what we're substituting inside the function already, then we can cancel it out. And this cancellation is very important. Otherwise, as you can see, sometimes if you can't cancel it directly, it's gonna be very difficult to integrate later. So this, I said that there are two options, right? So we can either substitute sine x or cosine x. And the reason why we could do both is because even if we substitute cosine x, we'll have the derivative sine x, and sine x exists, although the problem is we have 7 sines multiplied, right? But still, we have sine x, so we can cancel it out, and then we can use another identities to solve it. So this too is Very, very important. And if you don't have a derivative of what you're substituting in the original function, then for most of the time, unless you have another like identities, so for example trig identities or something like log or exponential properties, unless you apply them, you may not be able to solve the questions. So mainly these two, and then lastly, when you have a quotient, let's say, very rare to get. So for IGCSE students, you will not have something like this, but SL, it's possible, and HL, definitely. So when you have a quotient, try to substitute the denominator. Okay, so if you remember these three rules, three tips, then substitution wouldn't be that difficult. So honestly, for substitution, it's basically the most important thing is again the second one. So if the function doesn't satisfy this, then either you should try to rearrange the function so that you make the derivative of what you're trying to substitute, or you may not be able to use substitution to solve it. Okay. And for this question 3, I'll give you a simple example. So remember just now I said that integrating ln x is not easy at all. So just integrating ln x, well, you'll have this is the result, but it's very, very difficult to find this for SL and IGCSE, because you need to know something called the by part, which is for HL. But for example, something like this, then we can integrate it using substitution. So again, it's in the quotient form. So one thing is that we have 3 tips, right? Actually, we should rearrange the order. So you should look for this first. Okay, so I'll let this as one. So that's the very first condition that you must check. And these 2 and 3, it depends on you. So I mean, it depends on the question. So either if it's in the quotient form or the product form, then you can choose whatever you want. But for this one, so if you see that it's a quotient, so if you just think of this last tip, then some may substitute this, the denominator, right? And of course it will do nothing for you, right? So as I said, check this first. So let's check it. If you want to substitute x, then that means the derivative of x must exist, and which is 1. Okay, that makes sense, right? But the problem is, does that cancel with something else? No, it doesn't. And that's why it's just giving you the same result. So even if you do that, then everything is just in you. Nothing changed, right? So it's completely useless to do it. Then let's think of ln x. If we differentiate ln x, what do we have? We have 1 over x. And do you see 1 over x? Yes, we do, right? Because ln x over x is simply ln x times 1 over x, right? So the first condition is satisfied. And since we don't have like different powers, so let's forget about the other tips, 2 and 3, okay? Let's directly try this from here. So we let ln x as u, so we have u over x, and then by further rearranging this, we have du equals to du times x equals to dx. So x moves there, dx moves there, and we have this. So dx can be replaced by x times du, right? And we can see that x cancels. So it's simply integrating u by du, u by u. So deadly simple, right? Half times ln x squared plus c. That's it. Okay. So that's how we can use substitution to solve. So that's what I mean by this first tip. And for something like the powers or the denominator. Okay, for this last tip, I'll give you an example which is not really in your level unless you're in HO, but it's a very good example that I can think of. So integrating tangent. So integrating tangent, that means, so first it's not in a quotient form, right? Then why don't we just make it into quotient form, sine x over cosine x? Then it's in a quotient, so we can try to apply this. But before that, as I said, we have to check for this first condition first, right? So if we want, so let's say we try to substitute sine x, then cosine x must be inside it, right? Well, we do have cosine x, so maybe we could try to substitute sine x, right? And also let's check for cosine x. If we substitute cosine x, then sine x must be inside the function, and we have sine x too, right? That means we can try to substitute either of it, but using the tip 3, let's try to substitute the denominator. So we substitute the denominator as u. Okay, then let's do what we have been doing. So sine x over u equals to dx, not equals. So basically this, we can write it like that. And so the main part is that we have to change dx by u in order to synchronize the variables. So we can differentiate this, and by rearranging it, we have that. Alright, so we now know how to write dx in terms of du. So let's use that. Alright, and you can see that sine x cancels, right? So this is what we get. And this should be simple, right? Because integrating 1 over u, that means ln u. And we have a constant c. Okay, one thing for ln is that, okay, so since it's an indefinite integral, so it's not really important, but I mean it's still important. So one thing is that, can ln has a negative value inside? And the answer is no, if you recall the properties of log, right? So just in case, we put a modulus sign, okay? And just by further rearranging it, well, you don't need to rearrange any further, you just need to replace u by cosine x. But for HO students, you'll have a formula for integrating tangent x, which is ln secant x modulus plus c. And the reason why it's secant is that if we have a negative as a coefficient, if we have a coefficient after log, then we can put it inside, right? And then this becomes the power. That means cosine x to -1, which is 1 over cosine, and it's secant, which is the reciprocal of cosine. So that's but yeah, even for SO, you may be asked to solve this, but maybe you just need to leave it like that, and it's not that difficult, right? So that's how we can do it. And I said that we can also substitute sine x as well, right? Okay, I'll show what happens if we substitute sine x. Then u over cosine x times du over cosine x. So see, you can't cancel them out. well, you can still try to do it. So it's using trigonometric identities. So it's cosine squared, right? Cosine squared, that means 1 over sine squared, so 1 minus u squared du, right? And yeah, you can it's absolutely fine. You just need to use substitution again. Why? Because, so first, we have denominator, right? And it has higher power. So some may think that just substituting u squared into another variable should be fine to cancel out u, right? But why don't we just substitute the entire thing? Because even if the constant here is included, but if you differentiate it, it will just disappear and you'll negative 2u, and then rearranging it, you'll eventually have you'll have this, and it's exactly the same. You will have the same result, but again, I said it's the matter of efficiency and the time consumption. So for the second case where you have to substitute sine x, you have to use substitution twice. But if you just substitute cosine x, then you just need to use it once. So again, it's just a matter of time. So that's the main examples for substitution. And for every video, I'll post a sample test with some questions in different difficulties, and you'll try a lot more questions on there. Okay, so I'll not spend too much time on just explaining the examples. So that was it for the substitution, integration by substitution. And what else do we have to do? Okay, it has already been around 42 minutes, so we'll have a quick break, around 2 minutes break, and I'll come back again, okay? Alright, I think that should be it for 2 minutes, and let's resume with from where we stopped. So before the break, we've mainly talked about some basic integration formulas using antiderivatives, and we also looked for some of the integration of linearly transformed trigonometric functions, and solving by inspection and solving by substitution, and we've also seen some hard substitution questions. So now we are, for SL and IGCSE students, you're done with methods of integration, and for HO students you have a bit more, just a bit more, and this I will talk about in the later video. But yeah, before that, we're going to look for the main applications of integration. Okay, so like in differentiation, there are many applications of integration, and they are mainly related to areas and volumes. So, but the first thing is just very simple thing, finding the original equation given the derivative. So what does that mean is that, for example, if finding the original function with the derivative and initial condition. So what does that mean? Remember the way of antiderivative, okay? So if we have a derivative, so for example, f prime x equals to something like x cubed plus x squared plus 1, let's say, what does that mean by f prime x? It's the equation of the gradient. And note that f prime x is not independent to the original function. What does that mean? So using this differentiated function f prime x, we can find the original function as well, right? How? Because remember, using antiderivative, we have this, right? So if we have f prime x, then if we integrate it, then we'll have fx, the original curve. In other words, if we differentiate that, we have that, right? Then let's integrate this, and it's gonna be it should be very simple by now if you have done enough practice. So this is the original curve, right? But this c, the integral constant. So since this is an indefinite integral, we have to put c, but maybe the original curve is more specific than this, right? It should be more specific than this, because usually we will have with a constant, not with a c, right? So as I said, the initial condition will be given, and that initial condition is a point on the original curve. So for example, let's say the point was 0, 2. The initial condition is 0, 2. Then that means if we input 0, we'll have output as 2. So we can evaluate it, right? So 0, 0, 0, 0, 0, 0, we will have c only. And that means c equals to 2. Therefore, the original function will be like this. Okay, so yeah, as long as you can integrate a function, this shouldn't be difficult at all. Okay, so the main application is finding the area. And one thing that I want to specify, I want to recall again, is that so integration was mainly looking for the area under the curve, right? And we have all the examples in the beginning. I talked about the case where the function is always above the x-axis, right? But what if it's below x-axis? And does that matter? And of course, if I mention it, that means it matters, right? Then how does that matter? So for example, again, if we have to integrate the function between a to b, x equals to a to x equals to b, that means we are basically looking for the area under the curve bounded by this region, this boundaries. So what we are going to do is that we are going to do definite integrals now. And remember what definite integral is? Definite integral, that means you're computing a specific area under the curve given the boundary. So we're calculating the specific boundary, a specific area here bounded by this boundary. So how we can do that? So let's try some examples. Let's say we have a very simple curve like y equals x squared. And let's say we want to find the area between x equals to 0 to x equals to 2. So that means if we can sketch, that means we are finding this area. And one thing, for definite integrals or finding the area, sketching, if you can sketch, it's very, very good to sketch, okay? It's gonna be very useful. So, and the reason why I'm emphasizing about the sketch is that you'll see later in the another example, application, where you have to find the area between two curves, enclosed by two curves. But anyway, since we're just starting the area under the curve, let's just focus on this first. So the area here will be, so it's bounded by 0 to 2, right? And we're looking for the area under this curve, x squared, and we have dx. And again, what does it mean by x squared? It represents the length, right? Length of all the rectangles. And dx is the width of all the rectangles. So x squared times dx is simply representing the area of a small rectangle inside this curve. And we're at the integral means is that we're adding all those rectangles from where to where? 0 to 2, right? So integrating x squared, what do we have? 1/3 x cubed plus c, right? But again, we're adding from 0 to 2, right? That means we evaluate where it's all 2 and we subtract where it's all 0. And I'll tell you why we are doing this. Subtract where it's 0. And you can see that c cancels out, right? That's why for definite integral, you don't have to care about c, because it always cancels. But I'll talk about a bit more about this subtraction. So using what we know here, so if we integrate fx, let's say it becomes capital X fx plus c. Then what it means by fb here, okay, fb plus c, let's say, that means it's the entire area until b. So since I've just sketched until here, but as the function goes on and on, it's also including all the area there, but it's not really important right now. So let's just focus on this. So this FB represents this area, this entire area, okay? Then what's FA plus C? It's simply showing you the area until A. Until A. Because remember, what's the integrated function means? It represents the equation of the area over the domain, right? So if we put a certain x value, we'll have the area until that value, and it always starts from the left, okay? And this again it starts from the left, and then it's adding all the area until x equals to a. Then what happens if we subtract these two? Then we will just have this area, right? From a to b, right? Because that means we're simply crossing this out. Simply crossing that out, and then we'll just have that, and that's what we want to look for, right? That's why this holds. And so for definite integrals, it's basically you integrate the function and you evaluate for b, and then you subtract for fa, capital Fa, okay? And that means it's the area under the curve from a to b, okay? So that's how we can compute it. So we've seen a very simple case here, but of course, as I said, that's a very simple case. So what does that mean? Let's say we have something like a curve like this. So that's, let's say 1, 2, and let's say we have a function like this, okay? And we want to find this area. So let's try to use what we just learned just now. So the area must equal to the integral from 1 to a, and we're integrating this function, right, in respect to x. So we have dx, and again, that represents all the length, and this represents all the width, right? So in order to integrate this, don't treat this as a product of two different functions, just expand it out, because again, even if you have a product of functions, it's not like differentiation. It's very hard to integrate a product, okay? So never ever try to integrate a product directly, product of function directly. So we will have something like that, and then that will equal to a third x cubed minus 3/2 x squared plus 2x, and we have c, but we can omit it because, as you could see, c will always cancel out, okay? So what we can do is that we evaluate for the area where it's until x equals to 2, and we evaluate the area until x equals to 1, and then we subtract the 2, right? I mean, subtract those two areas. So for computation, a lot of students make mistake because it's a bit tedious, and like there are a lot of like fractions involved. So just do one by one carefully, okay? So that one is equals to 4, so cancel it out, you'll have 6 plus 4 and minus, okay, don't forget this 8 as well, and evaluate for 1. So this is what you will have. So that will give us -2, and then this is 8 over 3, so that's 6 over 2, so it will have 16 over 3 with multiplied by 8, because this inner part will give us 2/3. Does it? Yes, it does. And for this one, so that's 1.5, so it will have a half. So 1/3 plus 1/2, that's 5 over 6. So 5 over 6, 5 over 6. So we'll have that, and we'll have this. Do you think it makes sense? The area, right? We're looking for the area, and the area equals to -1/2, -4/3. and it doesn't make any sense, right? Because area is a scalar factor, which means that it has to be positive only. It cannot be negative. Then have we done something wrong? No, our computation is correct. Then what's wrong? So remember, that means, so that's why we have to understand the integral. So again, this integral, the very starting integral, means that this being the length, right? But length as in this y values, and that as width, and we are adding all those rectangles from 1 to 2. But let's look for the length first. What value of all these length? They're all negatives. But can the length be negative? No, it can't, right? Then what do we have to do? We have to make them into positive, right? And how do we do that? We can either put modulus, but if you're not familiar with modulus, what we can do is that we just flip it up. How do we flip it up? So what I mean by flipping up is that just change everything like that. And how do we do that? We put negative sign in front, right? Because remember, for quadratics, not only for quadratics, but if you learn some basic function transformation, so for any function like that, if you put negative on the entire function, not just x, entire thing, then it will be reflective over the x-axis. So that's what we are doing. So if we reflect this original function about the x-axis, then it will look like that. And then this area, now all the lengths here will be positive. The width is already positive, so that's it. That's how we can do it, right? Then everything we have put negative here, negative plus, so it will be 4/3, and it makes perfect sense. And that's how we can do it. So then let's say we have a function like so let's use the same function, but instead we are not integrating from 1 to 2. This time we want to integrate from x equals to 0 to x equals to 2. So the y-intercept must be 16. The graph is not to scale. I never draw them in scale, so this is how the graph looks like. And right, so for the area under, the reason why I emphasize on sketching is because you can only determine whether the area is negative or positive through the sketch. I mean, it's not the only method, but it's the easiest method without a calculator. So we'll have this, and what we can do is that we can separate them. So we just calculate one by one. So we just calculate this red region, and we calculate this blue region. And how? Okay, so this red region, it will be simply integrating from 0 to 1, and every length here is positive, right? So we can just directly integrate it, doing the same thing. And the blue region, so blue area, red area, blue area, that's integrating from 1 to 2. But again, as mentioned in this problem, all the lengths are right now negative. So what we do, we put negative sign in front so that it becomes positive. All the lengths become positive, and then we just integrate as what we did just now, and add these two up, and we'll have the area. So this is how we can find the area under the curves. Okay, so by sketching, through sketching you have to distinguish whether the region is above the x-axis or below the x-axis, and depending on that, the result will be very different. So you have to think of multiplying it by negative if the region is negative. Okay, so before we stop, One thing to remind you quickly is that so we have some important properties of definite integrals. Definite integrals. So, for example, let's say we have to integrate a function from a to b. So that means we are looking for the area under the curve of fx from a to b, right? But what if b is smaller than a? Then what that means is that so that's what it means. Okay, so b is smaller than a, but we're trying to find the area from a to b. So what we will have for this is first using what we know. This we have fb minus fa, right? And again, what does it mean by fb? So it's the area under the curve until b. So it will include this part as well, but for convention I'll just show you this because it will cancel each other anyway. This part will cancel out anyway. So yeah, let's just look for this part. And what fa means, we're looking for the entire part, right? This blue part. So clearly fa is bigger than fb. Then what you will have here is that you will have a negative value. But we're looking for the area under the curve, right? From this, between this b and a, right? Then how can the answer be negative? So what we can do here is that we can put negative sign and then we can switch back the boundary. So what you will have is that, so this is what you have. So that means, so if we change this back, we will have this, and that equals to this, right? So that means negative fb minus fa, right? So now we will have fa minus fb. Okay, so please remember that if the boundary above is smaller than the value of the boundary above is smaller than the value of the boundary below, then note that we can put negative sign in front and then we can switch the boundary. So then why do we learn this? So in what case do we have this? I'll give you an example. And with this example, there's a second thing that you have to know as an important property. So finding definite integral when we use integration by substitution. So finding definite integral with integration by substitution, when integration by substitution is used. So for example, let's say we want to integrate this function. Yeah, so let's say we want to integrate this function. So as what we learned from substitution, we try to, so first, in order to apply integration by substitution, you must be able to find the first derivative of the function that you want to substitute. So for example, if you want to substitute cosine, then that means you must be able to find the derivative of cosine, which is negative sine. Or if you want to substitute sine, that means you must be able to find the derivative of sine, which is cosine. Okay, so that means we can possibly use the either, but remember that it's better to use the one with higher power, right? So let's substitute cosine. Okay, then one thing, this boundary is for x, right? but we now made the substitution. That means we have to change this boundary for u as well. Okay, so how do we do that? So when x equals to pi, that means u equals to cosine pi, right? Which is -1. And when x equals to 0, then u equals to cosine 0, and it yields 1, right? And also, this dx, we have to change it in terms of u, right? So how we can do that is that we can differentiate this, and then we can rearrange this equation to find the equation of dx in terms of du. Now we're ready to integrate this. So what we have is that we will have boundary from 1 to -1. So that means we see that the upper boundary has a lower value than the lower boundary, like the boundary below, right? So we can apply what we learned from this first property, okay? So, and then let's just put everything back with what we made. So 1 minus u cubed, because we let cosine as u. And then this cosine will be u. And we still have sine x, but with dx, which equals to d over negative sine x, the sign will cancel out. And we have this negative sign, but by switching this boundary, we can cancel out this negative sign. Because remember, if we switch the boundary, we have -1, okay? So this is what you have to integrate. So you'll have half u squared minus 1/5 u to the 5, and then you evaluate for 1 to -1, okay? And then I will leave the job for you. So these are the two important properties of definite integrals you should remember. And for HL students, you learn one more method called the integration by parts, and then I'll explain how we can find the definite integral when we use the integration by parts, okay? So that's it for the video today. So bye.